Hello and welcome to part 4 of the video series about feature engineering, dimensionality reduction, feature selection, and feature extraction. In the previous part, previous 3 parts basically, we discussed mainly about what dimensionality reduction is, and particularly we talked about feature selection. We saw that feature selection is a mechanism that selects a subset of the original features that basically meet a particular criteria. In feature extraction, however, the goal or the motivation is not to keep the original features. I mean, that relaxation is there. And mostly the feature is transformed, or the features are transformed to new set of features, where the new set of features are smaller in number. So for example, if original features are 100, let's say, the new features might be just 40. But these 40 features are not not among the original 40 features. They normally are transformed variants or generated variants, created new features kind of stuff from the original features. So in feature extraction, the identity of original features, they basically they're lost. And sometimes you can reconstruct the original features if you really want. But in several cases, the reconstruction of original features may not be that simple, or sometimes completely impossible. So in this part, we will be basically focusing on one most powerful feature extraction technique. Basically deals with unsupervised feature extraction called principal component analysis. And in this particular video, I will be focusing on the motivation behind principal component analysis. And in the subsequent parts of this video series, we will be focusing on the underlying derivations and implementations in Python. So let's dive in. Principal component analysis actually is a very, very famous and very powerful technique in feature extraction or dimensionality reduction, in a way that it has a lot of properties. The basic idea is, if you have a lot of data points in a particular space here, for example, just think about these red points, these green points, these purple points, and these blue points. Think about these points scattered in a three-dimensional space, where the original space or the original feature space basically is three-dimensional. So that's, let's say, there are 3 dimensions. So dimension, let's say, X, dimension Y, and dimension Z. So let's say these are 3 dimensions of your original feature space. And all these data points, for example, this purple data point, it has 3 coordinates. So X coordinate, which means the projection of this point on x-axis, that's the X coordinate. The Y coordinate of this particular point is basically the projection of this point on Y coordinate. And the Z coordinate of this particular data point is actually the orthogonal projection, or the perpendicular projection of this data point onto the Z-axis, which I cannot show on this screen. Considering this Z-axis, so there is some projection. There is some projection on top of that. So these distances so this distance is X coordinate, this particular distance is Y coordinate, and similarly we have a Z coordinate. So we have axes, for example, x-axis, y-axis, z-axis, and each point, the number of x's, they actually are defining the dimensionality of the feature space, and each data point is represented by those many dimensions or those many numbers. For example, for this blue point, we have x-axis value, or the x coordinate value, or the x dimension value. We have a y dimension value and z dimension value. So this particular point is represented by 3 numbers: x value, y value, and z value. So these 3 values. Similarly, all these data points. So now if you think about all these data points, they have 3 dimensions, and they are plotted in this 3-dimensional space. Sometimes it is possible that the data that actually lies in a very high dimensional space, there may be a subspace inside that high dimensional space that the data exactly fits into that. Sometimes not exactly, but with a very few error, or with a good approximation that can be approximated by by a subspace inside the original parent space. Here I have shown an example. For example, assume all these data points like these red, green, purple, and blue, and assume a plane in this three-dimensional space. Assume this plane in this three-dimensional space. Plane in this three-dimensional space itself is a two-dimensional subspace. Technically, it is subspace if it passes through origin, but I don't want to go to the mathematical technicalities here. Just think about a plane that actually fits all this data very, very well. With a very few, for example, with a very few errors, if any. For example, this purple dot is no longer in the space, but it is very close to the space. So if I want to represent this point in this space, so I will be finding out eventually the closest point in this plane to this purple dot, and that might be here. And this then will be called an error. So the idea might be to find out a subspace inside a bigger space that minimizes the total error, which means it represents all the data or fits all the data as best as possible. And sometimes in high dimensional data, it is possible to come up with a subspace or the data has some structure such that there is a subspace that actually fits the data. And principal component analysis is a technique to find out that subspace. Find out the subspace. Obviously, in the parent space, if you have a subspace, its dimensions are smaller than the parent space. For example, here it's a plane in 3D. So plane has two dimensions. First axis is PC1, just principal component 1. You can call it as x dash axis, or this second axis is y dash axis. So all these data points in this plane, they can be represented by just two numbers, x dash coordinate and y dash coordinate. And so all these numbers, they can be represented by two coordinates rather than three coordinates, x dash coordinate and y dash coordinate. And so the dimensionality from 3, it goes to 2, and that's basically what is done by PCA. Here I have shown that if we represent all these data points in this plane, just it's a grid or the parallel view of this particular plane, then all these data points, all these data points, they have just two coordinates, PC1 coordinate, or let me call that as x dash coordinate, and PC2 coordinates, let me call that as y dash coordinate. So we have these kind of coordinates. So in principal component analysis, you have to find out a subspace that best fits the data. So finding out that subspace is basically the goal of PCA. So sometimes we need to find out the subspace that actually fits the data exactly well with zero error. But in most of the applications, we allow some error. We allow some error. Let's say we want to keep, let's say 90 or 95% or 96% of the information inside the data. And we may bear to lose, let's say 6% or 4% or 5% of the information by reducing a lot of dimensions. So the goal of PCA is given data, find out a subspace with smaller dimensions that actually fits the data very, very well. It turns out that finding out the subspace that best fits the data, actually find out the axis. By the way, the space or subspace, they are defined by their axis, or sometimes called the basis vectors. So what do you think? If you have this particular data, the blue dots, and that data, let's say, is in two-dimensional space. The original space is XY space. That's a two-dimensional space, let's say. If you're asked to just find out a one-dimensional space, which is just a line, that best represents these blue dots or the blue data, what kind of line you will come up with? You may come up with, for example, this line, this red line. But you see this red line, it does not represent all the data very well, because if I take projections on this data, there are huge errors. For example, these green lines, these are errors. The distances are so these are errors. So you can see these are huge errors. we are making a lot of errors. On the other hand, if, for example, I choose this particular axis, then you can see the errors for all the points that will be really, really huge. So if my goal is to come up with one-dimensional space that represents the data best, what will be that axis? What will be the direction of that axis? In this particular case, what will be the direction of that line? Well, it turns out the direction of that line is the subspace is the direction that maximizes the variance. See, in this particular direction, the variance of these blue points is high. So if I keep my direction of my new subspace in the direction of maximum variance, in which the data has a lot of variance. In this direction, the data is varying a lot. In this particular direction, the data is varying a lot. So the axis will be the axis that is in the direction of maximum variance. That will be the direction. And if I project all my data onto this particular axis, the guarantee is there is no other one-dimensional space that can better represent this data. So basically, PCA computes the axis of subspace with respect to maximizing the variance, because this variance is somehow the amount of information that is there in data, and we want to keep the axis that actually maximizes the variance. Here, if you see, if I'm allowed to choose only one direction, then I will choose this particular direction, because in this direction the variation of data is high. And if I project all my data into this subspace, the error will be minimum as compared to all other directions if I really visit to. So PCA can also be thought of as maximum variance preserving projection. It finds out a subspace that keeps the maximum variance, and here variance can be thought of as amount of information that is there in the data, and we want to keep that amount of information in the data. There are a lot of properties of PCA. PCA is a linear transform, which means if you have original data points x, let's say xi, in d dimensions, then there is some matrix here, some matrix that transforms the data to another data points. So think about this xi to be d-dimensional. Think this yi to be k-dimensional. So there will be a matrix inside which will be k by d that will transform this xi to yi. And if you can achieve any transformation, if you can achieve any mapping through a matrix multiplication, then that mapping or that transformation casually is called a linear transform. So PCA in its very basics is a linear transform, which means at the end of the day there will be a matrix that will transform original data to reduced dimensional data. Further, it turns out that as PCA preserved the maximum variance, it also preserved the reconstruction error, which means if you have projected your data onto the subspace, just take an example. If you have projected your data onto subspace and you want to reconstruct the data back using these axes, x1, x dash axis, and y dash axis, if you want to reconstruct your data back, think about this projection as compression. You compress the data, and now you want to decompress the data. So if you decompress the data, there is a way to decompress the data or reconstruct the original data, original features back. Then the error, the reconstruction error, when you reconstruct the data and the original data, their Euclidean error or the reconstruction error is the minimum. So under linear transformation, PCA gives a subspace that minimizes the reconstruction error. Also, under linear transformation, PCA gives a subspace that actually maximizes the variance of the projection. It also turns out, that the PCA, it actually preserves the pairwise Euclidean distances as well. So for example, if you have data, for example, this is a data point, that's a data point, that's a data point, that's a data point. The distance between these two data points, the distance between these two data points, and distance between these two data points, then we can have distance of this data point with this one, distance of this data point with this one. And then we can have, for example, distance of this data point with this one. So you can see all these pairwise distances. These distances are somehow preserved by PCA. And actually there's a whole different concept called metric multidimensional scaling that actually builds on top of preserving pairwise distances. So that matrix multidimensional scaling, if in that multidimensional scaling, if you preserve Euclidean distances, you actually land into PCA. And if you preserve some other distance measure, then you have other methods, other nonlinear methods for doing these kind of stuff. So PCA have a lot of properties. I mean, a linear transform, minimum reconstruction error, maximum variance preservance, and it preserves the pairwise Euclidean distance, or sometimes called the geometry of your original data. Yeah. So it turns out that PCA can be made nonlinear as well, and the concept is known as kernel PCA. In kernel PCA, actually, we built a kernel, which kernel is a matrix that sometimes represent the similarity measures or similarity between different data points. And it turns out that the PCA can be transformed to kernel PCA, which is a very, very powerful technique, and it actually supplies, rather than a linear subspace, it supplies a nonlinear manifold kind of stuff upon which the data can be projected, and all the other properties of PCA, they're preserved. Actually, in kernel PCA, what happens is the data originally, the data point xi originally is transformed to some other space, and in that space the PCA actually is carried out. So the linear transformation happens at the transformed space, sometimes called the Hilbert space. In that space, all the linear transformation that is carried out, but that linear transformation corresponds to some nonlinear dimensionality reduction in the original space. And that's very, very powerful technique, in the sense that there are so many other nonlinear dimensionality reduction techniques, including this metric multidimensional scaling. With Euclidean distance, it is a plain PCA. And in metric multidimensional scaling, if you use, rather than Euclidean distance, if you use geodesic distance, then this MDS actually comes up with isomap. There is a locally linear embedding method in which the original data is transformed by keeping the linear patches of the data. So the different patches of the data, they are assumed to be linear. They are assumed to be linear subspaces, and different patches of the data, they are actually, after assuming them linear, the dimensionality reduction carried out on those linear patches. And that is sometimes called locally linear embedding. There is other nonlinear method called Laplacian eigenmaps, which is very close to spectral clustering. It turns out that all these MDS, isomap, LLE, and Laplacian eigenmaps, they are special cases of just kernel PCA with different kernels. I mean, you design different kind of kernels. For example, with a specific kernel PCA, MDS is really a kernel PCA. With another kind of kernel, the isomap is really kernel PCA. LLE is really kernel PCA with a different kernel. And Laplacian eigenmaps is a different, is again a kernel PCA with yet another kernel. On the other hand, all these techniques, they rely on a fixed kind of kernel that is fixed as a hyperparameter, what kind of distance metric we are going to use. In maximum variance unfolding, sometimes called the semi-definite embedding, the kernel is learned from the data. So this kind of kernel is learned from the data. But after learning the kernel from the data, with that kernel that is learned from the data, MVU is also kernel PCA. So PCA is really, really, really powerful, and the kernelized version of this PCA, actually it has linked to several other nonlinear dimensionality reduction techniques, which at a first glance, they may not look connected to kernel PCA, but they all are one way or the other are special types of this kernel PCA. So I end this video here. I end this part here, part of this video series here, by just telling you that PCA is really powerful, and the kernelized version of this PCA has links to several nonlinear dimensionality reduction techniques, which make it much more powerful, particularly theoretically and practically as well. And it is unsupervised technique, although there are supervised PCA variants of PCA as well. In the next video of this series, in the next part of this series, part 5, we will actually be seeing the mathematical derivation behind PCA, how it actually maximizes the variance, and how the derivation derivation turns up. For example, given the data, if I set that I want to find out a subspace that maximizes the variance, how the derivation carries out. And in the next video, we will actually be coding PCA in Python from scratch, everything from scratch. So yeah, hope to see you in the next part of this video series.